So yeah, just because of the way this is going to be working, because of the hacky solution I just had to come up with, if I'm recording the whiteboard over there, well, let's see. If I'm going to be trying to record the whiteboard over there, you might be seeing my ugly mug up on the screen. But we'll see how that works out. Because they didn't exactly leave me a lot of whiteboards. This is not an ideal classroom, but the projector's nice. Projector is nice. Okay, so all your stuff is already on Canvas. And you can access Canvas by typing canvas.temple.edu. It'll bring you over here. You should have. So how many of you got an announcement on this? Yesterday. How many of you got an announcement yesterday in your email? Great. Did any of you bother watching the video that I put up? A couple of you. Okay, so I go over the syllabus, and of course, because my TAs have changed and the role of the other TA I have has changed, I'm going to have to update the syllabus, and I'll post an addendum to that. But essentially, the syllabus was slightly in flux. We're just redefining the late policy to be a bit more coherent. And but watch that video, because I'm not going to waste your time by going over the syllabus today, because it's Wednesday, and I need you to start writing a program to Friday. So, we don't got time to waste. The important thing on this page, by the way, is I try to be as, non-dependent on, whatever the school decides is their resources. So I try to go to, so first off, all the pages is your big resource. Class code, that brings up a link to GitHub, which is a website where I'll be posting all the code for the class. So every bit of code that I do in class, I'll be sure to upload it basically by the end of the week. Well, teaching week, so Wednesday, and then you'll be in the intro class. And of note, fall 2017. So there's all my code from last semester there too. So which will resemble a lot of stuff there. Let's see. Other thing to note is that I record my lectures, hence why I have something that a Twitch streamer would use on my laptop. And instead of using the proprietary software, I'm just dumping it into a YouTube playlist. So I'll try to upload those basically after class. But I'll be adding them onto a playlist, and if I need to do supplemental lectures, then I will. The only weird thing that might happen is that I might not be here Monday, and this might be turned into an additional lab kind of section. So this lecture on Monday, bring a laptop, and if you don't have a laptop, pair up with a friend who does have a laptop. And if you don't have a friend, make a friend. Let's see. So the entire, again, and the reasons that I might not be here on Monday is because I have jury duty tomorrow. So if I get called for a trial and that decides to go on over the weekend, I don't know how these things work really, because I haven't had to serve on a jury in Philadelphia or anywhere yet. So we'll see how that works. But if you are here, then Zhang Dong in the back will be here, and he's one of the TAs for this course, and he'll probably be here overseeing you guys. I'll put up a video over the weekend if I won't be here Monday, and then you'll be expected to watch that. So kind of be a flipped classroom, which is something I want to try. Any of you familiar with the concept of flipped classroom yet? No. Yes. What goes on in a flipped classroom?
So basically, on lecture, you post online, you expect to watch it online.
Yes.
And then you come to class and ask questions and things like that.
Right. The idea is that basically in the typical paradigm is that you do your homework out at home, right? Hence homework. And then in class, where the professor is, he gets up in front of you guys and starts talking a lot. I'm going to try to so worst case scenario for if I have to miss a lecture like that, we'll simply do a flipped lecture where basically I'll post something online and then you'll have an assignment here. How the assignments work and how they're broken down is in the syllabus video. Again, I keep referring you to that. So with that, let's go ahead and get started with what the heck you're doing here, which is you probably want to learn about computer science and programming, which are not necessarily the same things, but they are very related things. So I have, let's see, I don't have some slides, but I do have some lecture notes that I cobbled together over the course of a couple semesters. So let's see, not notes. And I'll post these online. Let's see. Oh, and the last thing is that this is class. Part of the reason I'm recording, the other big reason I've started recording my lectures is that this is being, is that we have a Japan campus and I have some students in Japan who are watching this, or at least I've been told I have students. I haven't actually checked my roster yet. Okay, so where did I put that? So did I not copy everything over? No, I did not, because it's been a crazy week so far. Here we go. This will, let's see, did I do anything for spring? No, so this will do it. This will have to do. And there's probably some things I'll have to change on the fly. So, all right. All right, so first off, I need to know, basically, is there anybody here who's programmed before or has experience programming? So, quite a lot of you. Okay, how many of you took 1051 here? Okay, so good number of you. A lot of you have programming from high school, I take it, or you learned on your own. So you might find this a bunch of review for the first 5 weeks or so, which is good, right? You know, that's an easy way to create a nice buffer for your grade. So as I mentioned in the syllabus video, but because it bears mentioning here, this is a very fast-paced course for the first couple weeks. I think we learn in like the first 5 or 6 weeks what I learned in basically a semester or a full year in high school. So we will be learning quite a lot of things very quickly, but we don't have to learn it so quickly that we can't go into like what is actually programming on here. But as a result, we do encourage all students who have not programmed before to maybe consider taking 1051 instead, or taking 1057, and 1051 I believe has plenty of slots open right now. 1051 is a gentler introduction that teaches you Python, which is actually my personal favorite language. If I could do this class in Python, I would. It is a fantastic language, and knowing more than one language won't hurt you. It certainly helps. It's really nice, and it goes over basically all the concepts you need to know for this one. 1057 is similar, but it's more geared towards the engineering students, and we do that in C, which is a different language that Java was derived from. There's this whole hierarchy, not hierarchy of language, but like, you know, sort of a genealogical chart. And all languages were like, oh, I like that feature, and they'll steal that feature from another language. And that's how languages get better, just by blatantly stealing or ripping off from other languages. All right, so first off, this is a CIS course, so Computer Information and Information Sciences. So we've got the question of what is computer science? Because a lot of you would think it's the study of computers, which would be the wrong answer. So what is computer science is a question I asked on the first exam. So you should know that. But I do give a simple definition, but I will have a simple definition for you. Okay? So computer science is no more about computers than astronomy is about telescopes. And I should know that because I've worked with astronomers before, and astronomy has to deal with a lot of heavy math, and it's not just about telescopes. But telescopes are nice, fun stuff. Biology is not about microscopes, right? Chemistry is not about beakers and test tubes. It's not about the tools you use to do the science, but it's very easy to associate those things. But because computer science is fairly new as a science, you know, as its own separate thing from mathematics, it's easy to get that confused. It is about how we use them and what we find out when we do. So this was a quote, and I've got it quoted over here. So as I mentioned, computer science is not the study of computers. The science actually doesn't, the pure actual science doesn't actually have too much to do with computers. But we do use them a lot. And it's not about programming necessarily, because that's an understandable misconception. because we are going to be learning how to program in this class, in this computer science class. So that seems a bit contradictory. I'm saying it's not about programming, but we're going to do programming to learn computer science. And this conception that pro-computer science is programming, completely understandable. That's what I had when I came in, and it took me until like maybe my junior year until I realized that was not the case. There was actually a lot more to computer science. And it isn't necessarily about learning programming languages. Computer science kind of existed, even though it wasn't defined, long before formal languages showed up. And by the time you get your degree, learning a new language isn't tough. It will take you a couple of weeks to really get into it, at most. And then, of course, you can spend years learning like the deep intricacies of any single language. But to learn how to use a language and consider it a useful tool, that should take you a couple of weeks, right? So, so the learning curve you experience here, like so much of the stuff, I'd say maybe 70 to 90% of it will transfer from one language to another. And then there's just little quirks that you have to learn along the way, and then you get those quirks out of the way, and then the rest is just deep knowledge, kind of black magic stuff. We don't study software. Like, we aren't going to learn how certain programs work, except for, very specific programs like compilers and interpreters. And that's not for that class, for this class, but those are like the programs we concern ourselves with. What's a compiler? What's an interpreter? We'll get into that in this lecture. So it's more easy. So we've easily defined what computer science isn't. What it is actually like coming up with a good definition. People yell at each other what the definition of computer science is, and I will give you a very simple answer. So, which is this one: Gibbs and Tucker. I like this definition, and I think this is my favorite definition. Computer science is the study of algorithms. Okay. So of course that answers our question. We've answered our question with a question. What the heck is an algorithm? Right? So, but we'll get into that. We have other definitions where we can break it down. Computer science is a science. It's a study of how we can automate problem solving. Okay? So that's one thing we want to do. We want to take the tedious tasks and we want to automate them. Okay? And not only that, we're going to do that with our own tools. Like a lot of the programming that we do these days, a lot of stuff happens kind of under the hood of your computer that had to be done by programmers maybe 60 years ago, and it was tedious to do these things. Now our life is made easier by these high-level programming languages. The question computer science answers is that automated question. It's when we get right down to it, can we automate? Okay? What can we do? What can we set up on a process so that something can just handle itself? And furthermore, which is a question we'll answer later, what can be efficiently automated? And this gets it, and this question really doesn't get answered until the senior year, until we get formal definitions. You have to kind of take a computer automata, which is a really heavy math/linguistics/computer science course to really answer that question. What can be automated? What can't be automated? There's this big definition of theoretical computer science, which is just one branch of computer science over here. It covers algorithms, data structures, computational complexity, parallel and distributed computation, probabilistic computation, quantum computation. That sounds scary. Automata theory, information theory, cryptography. Now that sounds nice and fun. Program semantics, computational biology, computational economics, number theory, algebra. So that's a very heavily mathematical field. That being said, what's the mathematical prereq for this course? College algebra, I think, right? Or is it pre-calc? I mean, it's the mathematic prereq for this class aren't big. So I have two very contradictory philosophies when it comes to math and computer science, right? On the one hand, math and your math skills should not get in the way of you learning how to program. On the other hand, becoming a fantastic programmer, something beyond great, requires you to be very comfortable with mathematics. That being said, learning how to program, math should not be an initial barrier to you. And the more you learn computer science, the more you learn how to think abstractly, the more that's going to carry over to mathematics. Okay, so this will help you with mathematics, hopefully. Okay. So what does it mean when I say that computer science is the study of algorithms? That means we are going to study the behavior of algorithms to determine if they're correct and efficient. So this is like the super formal definition. Studying the behavior of algorithms to determine if they're correct and efficient. Designing and building computer systems that are able to execute algorithms. Designing programming languages that can take your algorithms and turn it in and translate those algorithms into languages that can be executed by the computer. The computer only understands very basic things, such as zeros and ones. And it can really only do a couple things, like add two numbers together and store that somewhere and compare two numbers. That's really all it can do. Your computer does those, and that's basically all your computer can do. In identifying important problems and designing correct and efficient software packages to solve these problems. So what is an algorithm? An algorithm is a sequence of steps. You can think of it like a recipe. It's unambiguous instructions. So and this is the thing that you should really come to have a personal hatred of, a loathing, ambiguity. So you may have heard a couple days ago about the false alarm that happened in Hawaii, that basically everybody in Hawaii was running for their lives because somebody clicked the wrong link. I do not blame that person who clicked the link. I blame the programmer who programmed it so that it would be ambiguous whether a false missile alert would be set out or an actual missile alert would be set out. Programming has real-life consequences, such as almost accidentally causing a nuclear war. But in not jesting, it does actually have real-world consequences. We've had consequences where bad error messages have caused people to accidentally get a shot full of radiation and get killed by that, because the medical device that they were using had an overflow error in it, and the error was not appropriately expressed. So that's, I believe, the Therac 25, and I'm just butchering half-remembered thoughts. But look that up. It's a big case study in computer science. And that's what we need to avoid, ambiguity. So algorithms are unambiguous instructions, and they have a clear order, a clear, well-defined order, meaning you do one in front of you do one instruction, then you do another instruction, then you do another instruction. So clear, well-defined, unambiguous, ordered, and they also have an end. You don't necessarily do it forever. Come on in. All right. So this bit I wrote while I was still at another institution. What can you do with computer science? So this is actually where we get into the fun stuff. What can you do besides just being a code monkey working for a program, working from some big corporation and just hacking out apps, right? Or creating things that will entertain people or bombard them with information or try to get them to click on a button, right? So much money is being spent on on trying to get people like us to click on buttons. And when I mean people like us, I mean like all of humanity. That there's a lot being spent just trying to figure out, can we get them to click on something, right? So we can get advertising revenue. Okay? So it's not just creating apps, it's not just advertising, it's not just creating video games, although I love video games. Okay? We can learn to apply computer science to other fields. Biology, chemistry, and medicine. So my former institution, about half the department was in bioinformatics research. Bioinformatics sounds really scary, but all that means is that informatics is another term for computer science. So bio-computer science, you might understand that as biology and computer science put together. So that's doing some really important problems, like trying to cure cancer or analyze all these huge amounts of biological data we're doing. That cure cancer one's, though, a big one. Figuring out which, HIV retroviral inhibitors. So, designing new medicines. Oh, electronic prosthetics. Designing better robotic arms so that people who lose their arms in some accident can actually, pick up stuff or hold their kid. It's important. This has meaningful impact on people's lives. Okay? Physics and astronomy, quantum computing is a big research area right now. supernova detection, I've learned that basically that, we're getting huge amounts of data from the telescopes these days. And a whole lot of supernova detection is actually being done automated. So we're detecting new supernovas not by just, by the random astronomer looking. It's because we figure out that we've got somebody running an algorithm and they're like, aha, that signature, those wavelengths look like a supernova. So we're now going to be able to publish a paper saying we just spotted this supernova. Tons of astronomy data. So the Large Synoptic Survey Telescope is expected to gather 140 terabytes a day. That's something in space, giving us 140 terabytes of data a day. We need some way to filter that information and compress it and send it back to Earth and store it and analyze it. And those are a whole lot of different problems that are all too big for one person. Engineering, business and economics. So one of the things we do learn here, just unavoidably, is how do we work in teams. So we actually have entire manifestos, like the Agile Manifesto, on how we should work together and design software. Just so we have things like that. High-speed trading algorithms. So I have a lot of dollar signs over there because a lot of trades that happen on the stock market these days, not done by people, done by algorithms. And sometimes that causes flash crashes, meaning that basically the stock market just dips so much that it triggers a circuit breaker because these things are trading quicker than you can react to. One of my personal favorites, psychology, human-computer interaction, HCI. So this is basically how do we make user interfaces so that computers are easier for people to use. What's the value of putting, menus here versus here, those kind of things. One that I got into this when I was doing undergraduate research, where I was working on, I was working in a lab that worked on user interfaces and acoustical maps for blind users. So how can we use programs and computer science to improve the lives of people who can't see the screen? How can we do that? Education? Well, I mean, come on. I'm uploading this to YouTube, so you can see this at any point you want to. So huge educational value for that. And there's tons of computer science courses on YouTube from great institutions like MIT, that you can just look at for free. Edutainment, education and entertainment. So games that actually teach you stuff. And of course, just more direct applications, software engineering, networking, so figuring out how information travels from point A to point B, data analysis, and security, of course, which is a big concern today. Mind you, you probably heard, just as an aside, no system will be completely secure ever because we have one giant weakness, which is us. Humans are the weak point in any security system. Keep this in mind, right? How many times have you told somebody your login information, your username and password? That's a security risk there. Or if you worked for some company. I mean, I'm pretty sure that if a bad guy knew that you were working for this company, and you had access to X, Y, and Z that they want, well, they could just tell you, hi, we have your family hostage. You're going to give us your password so that we can get in and nobody's going to get hurt, right? And you're like, it's just data. So, all right. So just keep this in mind. The weak point in any security system, in any secure system is us all. All right. What is an algorithm? Getting back into this. So where does the word come from? It comes from the first historical figure I'm going to cover here. It comes from the Latinized name of Muhammad ibn Musa al-Khwarizmi. So they took that name and they're like, and of course they just Latinized that. So they just took al-Khwarizmi and turned that into algorithm. So we get algorithm from the Latinized name of algorithm. Okay, who was he? He was a Persian Muslim mathematician back in the 800s. So, and he wrote a book and did something that basically makes a lot of sixth graders hate him, which is that he wrote a book called the concise book of calculation by reduction, which was where we get algebra from, because that title part of that title translated was algebra. So of course that got Latinized as well to algebra, and that was an algebra book. So as far as I understand. So he also wrote a book that contained formal instructions on how to do mathematical operations on these newfangled Indian numerals, the ones that we use today, which are sometimes called Arabic numerals, which, are, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Those kind of things, those numbers, as opposed to dealing with I, V, VI, so instead of dealing with really annoying Roman numerals. Okay, so we named the word algorithm after him because he had these books on these instructions you should do to do algebraic operations and arithmetical operations. So as I mentioned, an algorithm is a well-ordered, unambiguous operations that yield some result in a finite amount of time. So well-ordered, again, meaning that these things have a clear order. You're going to do this, then this, then this. Unambiguous, meaning there's no confusion about how that's going to work, right? Like in a recipe, take an egg. Where we understand and intuit that should be, a chicken egg and not, say, an ostrich egg, So, actual thing you can get, I believe. So, let's see. Operations yield some result, meaning the algorithm does something. It just doesn't waste our time and burn energy. And it gets us a result in a finite amount of time. It's not a proper algorithm unless it actually, finishes. Could take a while, but it's going to finish. So some algorithms that we do know are basic arithmetic. So let's go ahead and see. If I change this to grab the camera, does that change over there? Okay, yeah, that's terrible, but whatever. So let's go over a very, very basic algorithm that you know. Okay? And I'm going to have to play around with this. I'll have to come in and play around with this and see if I can't figure out how to do this. So let's see. 573 plus 929. Right? The addition algorithm. Right? How does this work? We start at the ones place, right? We do 3 plus 9, so we add the ones digits together, and we calculate that result. It's 12 though, which is bigger than a 10, which is bigger than 9. So what do? Carry the 1. Carry the 1. Not your questions here. Right? So carry the 1, then add the carry and these two numbers together. So 1 plus 7 is 8. 8 plus 2 is 10. So that gives us 10, but we don't want 10. We want a single-digit number. So we take the 0, put it down here, carry the 1. 1 plus, I'll go ahead and do 9 because that's easier. That gives us 10. 10 plus 5 is 15. So 5, carry the 1, put the 1 down. So now, when you learned this was basically clear and unambiguous operations on how to do this, right? You do it in this way, and that to make sure that basically, you add the first number to the second number. You don't go back and say, hey, add the 7 to the 2, right? You don't do any of that kind of stuff. There's a very clear way that this works. That's an algorithm. Very basic algorithm that you know. Okay. Let me go ahead and switch back to my computer here. All right. So what a program is, so an algorithm might look like this one. This is Euclid's algorithm, one we'll study later in the semester, which calculates the the greatest common denominator. So it's a useful algorithm. So getting into what an algorithm is we're getting into programming. What's a program? We take an algorithm. So consider the algorithm kind of an outline. It's our way of, we typically write algorithms in English on our first go, or we think of them in English, like let's do this, then do this, then do this. And then we translate it into something the computer can understand. That's a lie. Actually, we translate it into something that a program on the computer can understand, and that program translates our program into something the computer can understand. there's a lot of layers of abstractions here that I'm going to actually have to lie to you a whole lot in this class. But that is the role of teachers. We lie to you until we can tell you a more clear truth. So programs are software. The machinery they run on is hardware. We take this program and we run it on our computer. So let's go into how do we actually write a program. And there's a lot more stuff you can read here that I'll put this on. But the first thing I want to do is just go over a brief history of computer science, because your first assignment will be making a very basic program and then going into detail. Then I want you to research a historical figure and have your program tell me some stuff about that figure. Which might also be a hint that might be a question on the exam, on the first exam too. Your first exam will be around week 5 or 6. It really just depends on the speed of the course. And your first timed lab will be around week 4. Timed labs are about 5% of your grade, and your first exam is 15% of your grade. So again, more details in the syllabus over there. So very brief history of computer science. Kind of started when we figured out, hey, numbers are hard and we need a way to keep track of them. So we created the abacus. The abacus, if you remember, that's that thing with beads and strings, and you move that around. And what it was is that it was a very basic way to just store data, and that data was numbers. And that's really what computation was. It really just cared about numbers for a while, and how can we store numbers. And there's a lot of figures I'm going to be skipping over here, unfortunately. But if you go to, I'll have to post a link to this, the Crash Course Computer Science series, which is done by Crash Course, who do wonderful video series. They do a great history video. So the abacus was not a computer. It was just the human, though, working with the abacus could become a computer. In fact, when we said computer for a while, I believe that like the first written occurrence was like in the 1600s or something. It didn't refer to a machine. It referred to a person who would do computation and calculations. Person whose job it was to actually do math. So the abacus was a tool basically to help you keep track of numbers and do addition and subtraction and other operations. So gear machines, though, operating those things was tedious. So back between the 1600s and 1800s, a lot of people got into the idea. So why don't we make a machine that automatically does this? Maybe we have to turn a crank or something to do this, but it does the counting by itself, right? So what they would do is that they'd have a gear, and then what way the gears were oriented, that represented numbers. So you have Pascal. So figures in that were Pascal, Leibniz, Babbage. Babbage in particular was kind of important because that leads us to Ada Lovelace. Babbage, he created this, machine that he wanted to create this gear-based. He had two different machines that he wanted to create, but the idea here was that you could print your output on paper, so that you wouldn't have to go and check the gears, would punch holes in paper so that you could figure out what the machine's output was. So that brings us to Ada Lovelace, who's considered the first programmer. You probably learned about her father in English class in high school, the Lord Byron, the poet. But Ada Lovelace is considered the first programmer. Babbage's analytical engine, it was something he designed, something he thought about. He created basically a machine that could kind of do its own. You could give it instructions on how to do the operation, so you didn't have to do it yourself. It would take the instructions on the paper on paper cards with holes punched in them, because that was semi-readable. Because you could kind of read the hole punch papers if you're trained to do so, right? It just takes a while to learn how to do it. It's not as easy as reading text, but it was something, right? It was something both the human and the computer and the machine could understand. So Ada, what she did is she published a paper on that, and in the notes she had like some footnotes like this, and I say footnotes, but it was pages long, about how you could use this analytical engine to do something really awesome and compute these Bernoulli numbers, which were useful for probability on this machine. And so she wrote about how this machine, though, could possibly be used to work on problems that use stuff other than numbers. Right? We were, for thousands of years, we were just considering ourselves with numbers. But then she said, well, we could actually do this with things other than numbers by just translating stuff to numbers. If I'm remembering it all correctly, which is my caveat here. So it was about 100 years ahead of its time. The next big jump in computation came to World War II, where basically keeping your orders encoded, it came to the point where basically humans natively could not break those codes, right? In World War I, you could lock some code breaker up or a mathematician up in a room for about 3 days, and he'd come out and be able to translate those orders for you. But it was the birth of modern cryptography, where basically machines had to be used to make these ciphers. So Ultra was basically the intelligence that was gained by breaking the German ciphers, if I'm recalling correctly. And of course, we all probably have learned from the Imitation Game about Alan Turing. I'm actually very pleased to say that he was probably not as crotchety as was as portrayed in the movie. He actually got along quite better with others. But his bum, which was this machine for breaking the German codes, that wasn't a computer. It was just a really good machine. But why is he considered the father of computer science? Because he came up with a formal mathematical definition for what a computer is. But this was like the efforts of automating code breaking. It had a real impact. Eisenhower basically said that it was decisive in an Allied victory. Estimates were that it basically shortened the war. The intelligence shortened the war by 2 years. So, first computers, it's kind of contentious. There's, you can make arguments for various machines whether they were first or not. I've always been taught that ENIAC was the first because you could actually program on it. It was the electronic numerical integrator and computer. Construction began in 1943, completed in 1946. It used vacuum tubes. It took up 1,800 square feet, which is enormous. That's bigger than my house. So it was primarily used for artillery calculations. It did a lot of mathematical operations. Then once the transistor was created, once we figured out we could do these with, do these calculations with electrons and wires, well, they started becoming smaller. IBM introduced the first personal computer in 1981, and then that began the trend of the true trend of miniaturization and putting computers basically not only into everybody's hands but into everybody's pockets. You carry around a computer with you at all times these days, with more computational power than what we had to land craft on the moon. And here we are looking at cat videos on it and sending cat videos to everybody else. But I mean, what else would we do? The internet is now, and the biggest change in that was the internet, which is a global system of computers that are networked, meaning they can talk to each other. That's the big thing, that we can have all these computers, and now we can send information. In fact, we pretty much use our computers just as internet machines these days. I mean, that's pretty much it. That's the role of the computer. I mean, so Tim Berners-Lee proposed the World Wide Web. It was an application of the internet. So the internet is this big network, and you can think, and the World Wide Web is actually just this giant application that runs on it. This interlinked web pages and documents. It's so large that we need that huge companies run these things called search engines, so we can find the content we're looking for on the web. All right, so smartphones was the next thing after that, which were little internet-connected devices that we always have on us. So now we have a glowy screen that we're all absorbed in. Not that that's a bad thing, because I know if I didn't have this, I'd have my head stuck in a book most of the time. So it's not really too much of a change, if you think about it. So miniaturization are the big things today, making computers smaller and smaller. and then scale. Basically dealing with problems that are bigger and bigger and bigger. So before I give a 30-minute introduction on how to start on writing our first Java program, let me just discuss how do we become a good programmer. Some people, just like in math, maybe it comes to people a bit more easy than not. But I disagree with the idea that that just innate skill is everything, because it's not. What matters is practice. I was not a great student for my first 2 years because I did not practice. I did not, really do anything outside of what was assigned to me in class. And you should do more than that. You should practice. If you have you should pick up the textbook and you should work on problems from the textbook and try working on that. Practice is the only way to become good at this. If I were to compare this course to any other course, I wouldn't say it was like a math course, although it's probably, it is content-wise closest, but in terms of what the expectations are, it's closest to a music course, where basically, if you're in an ensemble and have been in an ensemble, you know that basically what matters is that during the performance, you don't mess up, right? And programs are like that. You can't make mistakes with your programs, otherwise they're not going to work. But how do you get better at being a better musician? You practice. And I speak having gotten a music minor, so I play the French horn quite terribly. So I know what I mean when I say you got to practice. I am in full. I fully admit I am a mediocre French horn player, but I got from terrible to mediocre by practicing. And that's the point. You become a good programmer by practicing. There's this whole 10,000 hours turns you into an expert. And there's truth to that here. You have to practice. And you're going to practice a lot just by getting the assignments, but go out and do some more. And what you learn here, especially since a lot of you are freshmen, this is easily applicable to a lot of the science courses you have to take. A lot of the stuff you do in sciences, especially physics, I could solve this by hand, which you probably should because you're probably going to have to do that on the test. But I can probably write a program to check my answers. This kind of stuff is really applicable. All right. So with that being said, let's talk about Java. So Java is a programming language. There are many programming languages. C, Python, C++, C#, a derivative of C, Lisp, and all of its derivatives, JavaScript, which is not really related to Java. Let's see, Ruby's popular these days. Go is popular. There's a lot of different programming languages, but the fundamentals stay the same beyond them. So the big thing about Java and why it became popular is that, first off, it looked a heck of a lot like C, which is a programming language that has been around since the 70s and basically is pretty ubiquitous. So that was one thing. The other thing was, though, that Java does something where it has the Java virtual machine, which means it's just this virtualized computer, for sake of simplicity, that runs on your computer. So as a result, because it's this application it's just a program that gets written for everything, what happens is that you can take your Java program, write it write it once anywhere, and then you can compile it, which I'll get into. Okay, and then you can run it basically anywhere on any computer that runs Java. So let's go ahead and write our first program, and then we'll explain this process in more detail because I just glossed over it, and what you really need are diagrams and stuff. But first, let's go ahead and see how writing a program works. Now, I'm not going to use an IDE, an integrated development environment, to write our first program. I'm going to do it the old-fashioned way, which is opening up a really small, a text editor. So I'm going to use an old program called Vim, which, if you have learned programming before, right? If you're one of those who raised your hand and said you already know how to program and a lot of this stuff is useful to you, yes? Oh, no, I said one of those who did raise your hand, right? Then it may be worthwhile to, take the time to do all this stuff in either one of these old programs called Vim or Emacs. Just mess around with it like for an hour, for like 2 hours this weekend. And I guarantee it's going to be worth your time. These are very, very extremely powerful text editors. And I really should take my own advice, but I don't have the time at the moment. But you guys do. Okay, so let's go ahead and write our first program. Java. So Java programs and so Java programs are of this format. The name, hello, so that's the file name, .java, which is the extension. So so Java files end in .java. Okay, so now the one thing I don't like about Java is that I will have to just basically give you a bit of black magic at the beginning. I'm going to have to say, you must say and incant these mystical phrases in order to get your computer, in order to get to work, and I don't like having to do that, but by the end of the semester, you will understand what each of these magical words mean. So let's go ahead and start with the magical incantation. Public, class, hello. So that's the first line. So notice that this word, hello, matches the file name that I have, hello.java, okay? And then I have curly braces. So those are weird things that you may not have ever had to use before, but those are located close to the P and the enter keys. It's on your brackets, so they're the shift bracket keys. Okay, we call them curly braces because they're curly. And we're not really great at naming stuff that all the time, but So this just simply means that anything we put inside of these curly braces exists inside of hello. It's a way of just basically denoting this is inside of something. Okay, and now the other mystical phrase: public, static, void, main, string, args. A lot of gibberish there, right? So public, that's a word I know, right? But static, is that like static electricity or something? Void, are we like getting into Buddhism or something here? Main, okay, I guess that's important because it's the main thing, okay? Are we dealing with like weaving here with strings? And what's with the brackets over here? Args, are we pirates now? This is just a bunch of black magic going on, but these are the things that you have to write down to get your to start with a program. And it's just what you have to deal with here. So all right, but now that we've got all this black magic done, we can start by actually running our program, and we're going to do the most basic thing we can do, which is have the computer talk back to us. So the way we do that, the way we get a computer to tell us something, is that we say system.out.println. So this will, and then quotation mark, hello, comma, world. Let's make it a bit more happy with an exclamation point, right? I'll just write. Okay. And so this is our first complete program. It is called Hello World. It is the program that basically gets written to begin in every programming language. Now, not every programming language has this much verbosity added to it. Like the way it works in Python is you just say print hello world, right? But on the other hand, a lot of programming languages, especially older ones, were also kind of harder to deal with, especially if you were trying to work with, something like assembly. Ugh. This is annoying, but basically, there's two lines here that we need to know about. The public class hello, and all you need to know is that your programs all start with public class hello. Well, not hello, but if my program name was foobar, it would start with foobar over here. If my file name was, dance, it would be dance. Public static, so here is what we call the main method. A method is just like a mini program, and we're going to learn how to write our own methods here. So public static void main string args. Arg stands for arguments. We're not going to really deal with them right now. A lot of these things we'll learn later. But once you write this, anything that you write inside these curly braces will get output. Now the spacing here, unlike Python, the spacing here is optional. For those of you who haven't taken Python, what that means is that basically the curly braces are the way of Java knowing what a paragraph is, essentially. Okay, and the semicolons here are the way of it's the way that Java knows what your sentence, how your sentence ends. So think of your semicolon like a period. Why aren't we using a period to end our sentences in Java? Well, they've already been used in other programming languages, and we didn't want to change that, where basically you use those to look inside of stuff. So we're looking inside the system, we're looking inside the outstream, and we're asking for the print line command. So system.out.println, this is the command to print something. So let's go ahead and see that it works. So I'm going to run. So now what I've done is that I have written a program in Java. Okay. Now I'm going to go and navigate to that file in here, and you notice that it's over here, and it's human readable, meaning that I can open it in something like this is what we call text. So I can open it in a very simple program like Notepad, right? It just shows up. I could have written this in Notepad. It's a bit tiny to see here, so maybe let's see this. But this is the same program that I wrote with the same spacing, okay? But I can't just go and hand this to the computer and say, run this, because the computer's going to go like, what's this? I only understand ones and zeros. Beep boop, So this isn't helpful. What we need to do is translate this into something that the computer can understand. So we use something called the compiler to do this. So we go javac. So the first thing we do is we call the command javac, and you have to do that. In order to do this, you have to have Java set up on your computer. I'll get into the easier way to do this, which is how we're going to do this in a second. So javac hello.java. And what this will do is that command says, let's take this. It runs a small program called a compiler. That takes the first program. Sorry, that takes our program and turns it into something that's a bit more manageable for our machine to understand. It translates it into commands. So this produces a new file. This is called a class file. Now the class files are the really cool feature of Java that we like, which is that basically I can take this class file and put it on any computer that could run Java, and this will work, right? So like a .exe file on my Windows machine, that won't work on a Mac, and that won't work with on a Linux machine. Well, it might work on a Linux machine if we fiddle with Linux quite a bit, because Linux is fun like that. But generally you can't just run these specifically designed programs on other machines. Java, though, because we're using a virtual computer on our computer, we can run this class file. Let's actually take a look at what's inside of here. What's inside this class file? So we said we translated this to machine instructions. So why don't we actually look inside it? Actually, I'll use Vim again. Vim hello.class. Okay, it's a bunch of gibberish, right? Unsurprisingly, right? I don't know what this says, but we can look around and we can understand a couple things. And I guess maybe that means start or something? The source file. Oh, hey, there's the name of my source file over there. Oh, hello world. I typed that, right? So there's some stuff in here, but mostly it's just gibberish because it's commands for the Java virtual machine to understand. Okay. So now what we can do is that we can take this command and we can pass it to the Java. We can run it in Java just by typing Java and then the name of our class. We don't say hello. We don't do hello.class. We just say the name without the extension. And prints out hello world. And it gave us a little space because what println does is that prints it out and then it gives us a new line. It gives us a new line for that. So let's go ahead and try some other stuff. So let's go ahead and just quickly modify this. Vim hello.java. Okay. Okay, let's see. I believe it's... Oh, yep. Okay. System.out.println. Welcome to 1068. Okay. So, now mind you, if we run this again, Java hello, it just prints out the same thing. Because when we change our program, we have to recompile it. So we recompile it, and then we run it again. Hello world, welcome to 1068. Now the thing about programs is that they're a little finicky, and they do exactly what you tell them to do. So if I accidentally made a mistake, like I left off a semicolon and saved it, and I tried to compile it again, tried to convert it into instructions, well, that doesn't make syntactical sense to the computer. So it gives me an error. It says, error on line 5, we're expecting a semicolon. You didn't have a semicolon there. And so I have to go back in, and then I have to fix that problem. So Vim hello.java. Okay. Okay. And then if I can compile it again, and it works. Okay. Now this process is pretty tedious, which is why a lot of you probably won't want to program like this. It's a useful thing to know that this is how it works, because what we really want to do is just work on this, all at once. So, your computers have something called. So the computers in lab will have something called an IDE installed on them. It's the one we have is NetBeans, I believe, installed, but I think Eclipse is also installed on them. I'll be using Eclipse. I'm sure a lot of you will probably use NetBeans. And what you can do is you can just download. You can go here, click on download, and let's see, I'm looking. Yeah, so here, if you click on this link down here, it will download both Java and NetBeans for you at the same here. It will take you to oracle.com. Oracle's the one who's in charge of Java right now. It will give you the previous version of Java, and that's just simply because the latest version of Java, which came out in September, I think it came out in September, doesn't actually work with the latest version of NetBeans, but that's fine. That's fine. I will be using Eclipse, so let me go ahead and show you what an IDE looks like. Okay? So, Eclipse. So the advantage of using a small program like I was doing that was that it's really small and you can pretty much run it on any computer. Okay? Now this program like this one, Eclipse, I saw it and it was like eating up like a gig of memory last time I was using it. So these things do use up quite a bit of memory, but they're extremely powerful. It's gotten to the point where you can actually have like a web-based IDE. So if you have trouble like with your laptop and it's not up to the job, speak to me and I'll be able to figure out some kind of solution for you. It doesn't matter what kind of laptop you have, so long as it's not filled with malware and stuff, you should be able to program on it. So the way IDEs work is, so an IDE is an integrated development environment. And what it does is that it simplifies the development process for you. So in Java, in Eclipse, it's organized into projects. So I'll create a new project called Hello to replicate what we were doing here. Okay, so we create a project. It's called Hello. And then we ask to write Control-N for new, or you could just simply go up to we can either right-click here and do new class. So that SRC stands for source. That's what we call the stuff we write, our source code. We can right-click and click on class, or we could go to new class over here. Either way it works. I'll just go over here because we're already here. New class. There's a lot of other options. You don't need to worry about them yet. Okay, and now we can type in the name of the class we want to write. You can name the package whatever you want, this project whatever you want. A project is simply just it's literally a folder on your computer, okay, that you can go to and find. So hello.java don't need to type .java. It will automatically add that for you. And then there's a bunch of stuff you can already add on there. But what it will do is that it will start writing the public class for you automatically. So notice that basically that you've got that this worked in Vim 2 where basically some words are different colors. This is what we call syntax highlighting, and it makes your life easier because it basically helps you figure out what is what. So public and class are what we call keywords, which are special words in Java that are reserved. So here we write our magic phrase, public static void main string args. And notice that when I hit enter, it automatically put in another curly brace for me. Right? It assumes that if you want to write one curly brace, then you're probably going to want the closed curly brace. As you get more experience with programming, nothing is going to cause you more tension and stress than seeing this. Let's see, can I even delete it? Yeah, than just seeing this, essentially, a single open parentheses. Right? These things will need to be balanced, and it will cause you a lot of stress just to see them unbalanced. So it stopped it right there because it was running something for the first time, which is that one of the great features of IDEs, NetBeans does this too, and NetBeans is a bit easier to use for a beginner, if I recall correctly. System.out. As I'm typing, it's coming up with suggestions. Print line. I know it's tiny to see. I have to figure out. I'm going to spend this weekend figuring out how to enlarge it because the scaling in Windows is terrible. So I'm going to try to make it more readable for you guys. The text is readable, but what is coming up is coming up with suggestions for autocomplete over here. System.println. Okay. And again, I put in a quotation marks, and I typed it once, and it came up with the other one because it assumes that, hey, if you put one in, you're going to want the other. And then when I typed the other quotation mark, it just moved beyond. And now rather than compiling or any of this, what this program does is that an IDE automatically compiles this. It automatically compiles it, and what each IDE does depends on that specific IDE. Eclipse automatically compiles it whenever you save it. So I've kind of developed a reflexive Control-S twitch, like if I type a couple lines on anything, be it a Word document or whatever, I instinctively hit Control-S, which is really annoying if I'm on a web page and I'm typing something because then I'll try to save the web page and I'm like, that's not what I wanted. So, all right. So now to just run it, I just hit this green arrow button and it runs and it comes out down here, hello world, right? So none of that hard having to remember what commands are. This is how you're going to program pretty much for a while. Some professors would make you like just work with the other ones and handicap yourself, but it's nice to know that these things exist. NetBeans works in a similar manner. So you just run this, hello world. If I want to make this a bit crazier and add 4 exclamation points, a sure sign of sanity right there, I can change it, just hit the run button, and it'll save it and run it. Another cool feature is that if I accidentally make my mistake there, right, it highlights that area I made a mistake in, right? Syntax error. Or if I misspell something like system.out, system.out.println, right? So a lot of errors in this one. So it's like, so I don't understand what system is. So you're like, oh, I'm terrible at spelling. Oops. So it's like, hi cannot be resolved to a variable. Oh, I must have forgotten to put these things around it. And then println. Oh, right? So it highlights for you the errors. Now, your goal when writing, and I see this is the biggest, if there's a problem I see with people who start programming, the biggest problem I see is that you'll write this or something like this, and then you'll continue on and you'll say, I'll get back to that later. Don't get back to it later. As soon as you see an error, get rid of it as soon as you can. Because if you don't know why that error is occurring, you should probably, if an error is occurring and you leave it there, the only reason that should be be the case is because you know why that error is occurring and you're about to fix that error in a couple lines. Okay? You should not leave any error coding, and you're going to see as I code that I don't do that. So your first assignment is actually kind of just familiarizing yourself with the interface. So you can work on either the lab computers or honestly any computer on campus should have this stuff on there. Or bring it to your computer to lab. If I'm not chosen for jury duty my goal is to be at basically every single one of your labs. Now, unfortunately, your labs overlap with another one of my labs. So I'll be at basically each lab for about an hour. So I'll be there and I'll help you get set up. I'll also be there to help with the homeworks as well. So and so I'll be there to help you set up stuff. So do I still have any of the other stuff there? No, I do not. So, what you want to do is download an IDE. You can either download NetBeans, which is recommended for beginners, or you can download Eclipse, which is a bit more industrial. I think I started with NetBeans myself or something like that, and then I moved on to Eclipse like halfway through the semester. If you already know how to program, learn how to do maybe just spend this weekend trying Vim or Emacs. There's tutorials that are built into both of them. They're very powerful, but they require a bit of a learning investment. But honestly, going and messing around with a random piece of technology or random program or random programming language is possibly the most valuable thing you can do at the beginning of the semester if you already know some stuff. So let me just go into detail on show you what your first assignment is going to be. It'll be due in a week, and then I'll dismiss the class a bit early. So your first assignment will be as follows. Basically, I want you to, this will be posted online later tonight. You need to install Java on your machine. So if you have a laptop, and I highly recommend you have a laptop, okay, bring it to class so you can install Java on it. If you do not have a laptop, and you cannot afford one, please speak to me because you might be over budgeting and think you need to spend $1,000 on a machine, where in reality a good computer that doesn't require any kind of special solutions might cost you around $350, and a computer where we can come up with a hacky solution would cost you around $200. So what you want is to create a new assignment. And what you're going to do is, rather than printing out Hello World, I want you to write a short 3-sentence biography about a famous computer scientist who is not named Turing, who is not named Gates, and who is not named Jobs. So I want you to print out each sentence on a separate line. And for reference, I've got the Hello World program listed for you here, so you can use that as a guide. So if you can successfully complete the task, then look up how to take user input, how to ask the user a question and get a response from the user, so in other words, look up how to use Scanner. And here's your grading rubric. So 90 points for actually doing this assignment. 10 points will be for proper code indentation, so making sure that your code is indented and it looks clean. Because, as I mentioned, white space doesn't matter. So a lot of times I see students doing something like this, where it's like that, which isn't too bad, but even worse, I see something like this, where basically it's all unindented. And the reason you want it to be indented is that it's easy to see, as a visual indicator, to see what's part of the same code block, which is the equivalent of a paragraph in English. Okay? So we'll go into more detail on that on Friday, and your TA will be able to correct that for you, so you can fix it if you try to turn it in. And again, 3 extra credit points for doing input with Scanner. All right, so I will end the lecture now.